What? Wait. We got about 5 minutes. Gonna wait for some people to come. Today we are going to be looking at coding. Now, there's several sides to coding. To the robot, we have to code not only the mainframe, which is the ROS operating system, but we have to be able to integrate everything into a language that the mainframe can understand. That means converting 4-wire sensors into code into the mainframe. So we're going to take a look at that. I'm going to be using the Arduino for that, Arduino Mega. And I'm going to show you a couple tools. We're not going to get to actually implementing anything today. I'm just going to show you a couple of the tools because, you know what, they just came today. So I haven't had time to put them together and do a full demonstration. But I've been charging a couple of batteries, and you'll see how many in a few minutes. In the effort of making my own battery for the robot. So we got a little over 3 minutes. Let's see who's joining right now. Launch. It doesn't seem to be working. It worked last time. Yeah. Two 2 minutes and 30 seconds. Hopefully there's some people coming on. Oh, you know what I didn't do? Shoot. I gotta make a title for this. Got 2 minutes. Live stream number 5. Hopefully that actually worked. Oh my goodness. There we go, less than a minute. Let's see what this looks like. Oh, sweet. Alright, cool. Alrighty then. Less than a minute. I hope there are some people. Let's go to the chat. Trying to get the chat open so that I can see what people are saying. Alright. Looks like that worked. Okay, reload page. Let's see what's going on. Yeah. Hopefully that's working. If I don't see your chats, I apologize. I'll reply to them later. I have no idea what's going on. with this. I'm using a new service, and they have a chat that says, I'm going to launch that. Apparently that worked. All right, let's get started. Here we go. Alright guys, welcome to another live stream. Today is August 24th. It is 7:08 p.m. and welcome. This is live stream number 5. Today we're going to go over some of the Arduino code that I just wrote today. And I'm going to show you how I'm going to go about making a large battery for the robot so that it can go a long time without charging. Let's see what's going on. I'm gonna go with the computer here. We can see a whole bunch of stuff. I don't know what this is. Alright. So here we go. In this screen here, you can see that I've already been charging a whole bunch of batteries. I made a charging dock that houses about 16 batteries at a time. I've been charging 16 batteries at a time. I did that a couple times, morning and night. So these are all fully charged, and these are actually all fully charged. I'll put these in here. But I wanted to charge a few more. I'm going to be making 2 battery packs at 36 volts for the robot. And depending on what the capacity check comes back as, it could be anywhere from 4.4 amp hours to 5.2 amp hours. Times 2, so 4.4, 8.8, or 10.4 amp hours, depending on what these used cells come back as when I actually test them. So what I have to do is I have to charge them up, capacity check them, charge them up again, let them sit for about a week or so, and then test them again. That's the burden of what you have to do when you actually use used 18650 cells. Now, if you're not familiar, 18650 cells are actually they come from laptop batteries basically, and what they do is, all laptop batteries have anywhere from, I would say, 5 to 7 of these. I had one laptop battery that had 9 of these. That would have been an awesome laptop battery, to tell you the truth. But these right here are 18650 cells. They're 3.4 to 4.2 volts each, with 2200 milliamp hours, so 2.2 amp hours. These are awesome batteries. So if you just for instance, you put 200 of these together, in a 24-volt configuration, you could power a refrigerator and an air conditioner for 3 hours. So a friend of mine and I, we put a bunch of these together in a case similar to the case that you see on the robot, and sent that over to Puerto Rico when they were out of power. And a bunch of families that had infants and babies, hence the name Cerebral Dad, infants and babies, were able to turn on the air conditioning, turn on the refrigerator, keep everybody in the family healthy for 3 hours at a time, and it was solar powered. So they were able to recharge during the day, and during the night they were able to have AC and all the amenities available to them in their home for 3 hours. So that was amazing. We did 2 of those. We sent them over to Puerto Rico, and we just built them and sent them. And we've gotten... you know what? I might share that on our channel. I'll read one of the letters. But it was just an amazingly rewarding experience for me to put the knowledge that I have about electronics and whatnot to good use to benefit other people. I'm getting off track. Where are we? We're cobbling together a robot. Yeah. So what I want to do is...
I can't hear this.
What's wrong, baby?
I can't hear this. What?
Why can't you use that? Looks like it's working to me. What's wrong? Oh, you can't hear it? Is that what it is? Volume down? How's that? Give me a kiss.
Yeah.
Daddy loves you. Hey, this is a live stream. Family stuff happens. Life happens. That's my daughter. She's amazingly cute. I love her. You should too. Alright. So here we are with a bunch of batteries. They're charging. Well, they're not charging right now. I gotta take these out, put new ones in. These are the new ones. See? I keep them all together. These haven't been charged, haven't been tested. But I do want to show you what I did with, wonder if I can make this bigger again. Can you see that better? Yeah. Okay, so I'm making my own Arduino library where we have, I have a battery class, I have, where the heck is everything? Okay, I have a battery class, I have status lights. Those are the 2 lights that you saw on top of the robot. There's a yellow one and a blue one. The red one stays on as long as the power is on, but we can do whatever we want with the yellow and blue one. Let's see if anybody has joined us so I'm not completely rambling on to myself. Hello, Michael. Hello, welcome again. Hello, Todd. For those who don't know, I stream on Twitch, Mixer, Periscope, and YouTube. Soon to be coming to Facebook Live when it's feasible for me to pay for it. I'm not going to pay for it. Mm-hmm.
What?
Yes.
Can you wait my butt?
Did you guys hear that? I will be right back. Daddy duty's call. Hold on. As I said before, life happens. I'm apologizing, but I'm not. Okay. So let's go through the code. I have this class that I called the KB Ross Robot, and it implements another class called Battery and Sensor Lights and Motors, which isn't fully developed yet. But what we can do is we can control the battery through here and the lights through here. And we can, oh, sorry, you can't see that. Let's see, camcorder. So the battery, we initialize it, excuse me, and then we initialize the lights, and we send it the locations. Right now I have it at pin 44 and 45 of the Arduino. So we have the battery and the lights that we can control through the Arduino. So let me close this. This is what the battery looks like. The battery here, this is the header file, and this is, we have ROS going in, and we have, what it is it's a cell monitoring system. We plug the battery into the Arduino using a voltage divider where you have VN and V out, because the battery of I can speak. The battery voltage is 36 volts, but the Arduino can only handle 5 volts. So what we do is we use a voltage divider to basically divide the voltage into 5 volts and use a multiplier to figure out how many volts are actually being represented by the battery. So what that looks like is we have this multiplier here. We have K, which is the impedance percentage. We have the cells, which is, we have 6 cells. Max cells is 12. Critical is 30%. I have yet to implement that, but critical means when it gets to a 30% capacity, I want to send a text message to my phone to alert me that the the battery is going dead, and I can charge it up. Eventually I have an automated charging station, but with 2 toddlers in the house, mains voltage and high 36 volts with 2.5 amps or 5 amps going to it just doesn't make sense. So if you go over to the actual code here, what it does is it takes a node, it advertises it to battery state, which is a standardized node in ROS, which is awesome. This is why I love ROS. It has so many standardized nodes. We can look it up and say battery state, that capacity, which is 2200, that I just made that up. 2200 is like an RC airplane uh, LiPo battery. I just made those values up to test it. And then we have a location, which is crawler, which comment below if you think crawler is a good name for the robot. I've been calling it the robot for so long. I might actually give away a couple stickers or a couple magnets if somebody would actually want to name the robot. Let me know if you want to name the robot. Comment below. Let me know. Serial number completely made up. I don't know what that is. So what we have a public function which is update battery state, and this would go in the main Arduino code in the loop function if you're familiar. So what we would do is every time the loop function iterates, we would update the battery state, and we would get all of this information and calculate it based on the battery that's plugged into the Arduino. There's a lot. So basically for a 6-cell battery, there are 7 voltage dividers, because for each cell you need a voltage divider, for exception of the first cell, which was 3.3 volts or 3.7 volts. So you have the first voltage divider, 3. Well, we can go up here and look. We got the first voltage divider, that is 3 here. And then we got 7. And then 10 and 11.2, but I made it 11. So these numbers are all by trial and error. Plugging the battery into another Arduino. I haven't actually made the robot's Arduino into a battery monitoring sensor, but this is the first step. So that's the battery. The main program is also representing, not representing, but asking about the status lights. So the status lights we have here is we initialize it with locations which has the number of lights, which is 2 in our case so far. We have the yellow one and the blue one. The blue one being like the Alexa skill, and the yellow one for all the warning signs. Like, I'm getting too close to something, let me blink and show you that I know that I'm getting too close to something. Because as the robot is running and the computer is not right in front of your face, as you make a more autonomous robot, you need a visual cue for it to tell you what it's actually doing. So we can do that with blinks and pulses of LED lights, sort of like, not really Morse code, but you can say if it blinks 3 times a second, then you know that it does something else. Or if it blinks 7 times every 2 seconds, then you know that it does something else. So that's a visual indicator of what we're actually doing with the robot. Okay, so as you can see, I have a blink state and a pulse state. The blink state has a location, meaning what pin the LED is located, an interval of how long you want it to stay on and stay off for. It's proportional right now. I can add to it later, but this is the bare bones right now. So let's say you want it to blink every second, so it would be a second on and second off. So you would set the interval to 1000 because it's in milliseconds. And then the count. how many times do you want it to do this? Do you want it to blink once every second for 9 seconds? Then you enter a value into the count. And a pulse means it fades in from 0 and it's full brightness, and then back down again, and in full brightness and back down again. So then we have a location for which LED we want to pulse, whether it be the yellow one or the blue one, an interval of how long you want the pulse to go from 0 to full brightness, and a count, how many times you want it to do that, right? And a speed, so it can go from 0 to full brightness in 3 seconds, or you can say, I want it to do it in half a second. And we can set that speed here. Now, there are certain times during the process or during the robot's cycle that we want to be able to turn the LEDs completely on or completely off. So what we do is we say, what LED do we want to turn on? Which LED do we want to turn off? And the bool, the state, is either true or false, on or off. And this is a little bit of what it looks like. Let me move this over here. So over here, the definition of these statements is, I gotta go to the status lights, sorry. Let me go to status lights. Okay. So we have blink. So basically what you do in Arduino is you blink something, you set a delay for a certain time in milliseconds, and then you turn it back on again or turn it back off again. But if I implement a delay in our Arduino code, that means that for that time, nothing is working. So I didn't want to do that. So I wanted to, they have a method called millis, which gets the milliseconds at that point in time during the running of the code. Excuse me 1 second. Yes.
Dad, where'll Mommy go?
She went to the football game with Logan.
But it's dark.
It's getting dark. Yeah, you're right.
Did you hear that?
Yeah, who's that?
I'm going to check out the window.
Go check out the window, okay.
Not this one.
Okay, take this with you. It's my daughter. I love her so much. She's so much fun. So the blink, what it does, without using a delay, what you do is you take the milliseconds. So you you initially set it to 0, right here. Previous milliseconds is 0. So you take the previous milliseconds, 0, current milliseconds, and then if that interval is greater or equal to the difference of the two, then you reset the previous milliseconds. And then you check the state of the LED. If it's low, then you turn it high. If it's high, then you turn it low. So you're blinking it on and off for a set interval, a certain amount of times, which is awesome. Pulse, exactly the same thing. You take how many times you want to blink it, you get the milliseconds, you convert it, but you do some fancy math in the middle, which you use the cosine of pi, 2 times pi, which is a good random number to use, and an interval and a speed minus current milliseconds. So what it does is go what it does is it fades slowly in the beginning and faster at the end. So it goes like this. And so that's sort of like a pulse of light, similar to Amazon's Alexa. When you address her by name, her lights go sort of on like this. They don't blink on, they sort of pulse on. So what we can do is, based on the topic or the message that is being published, we can pulse the lights on, giving it a little bit more of a heartbeat, giving it a little bit more of life, making it a little bit more tactile visually. So that's what that does. And then we set it on and on or off, based on the status that you give it. And you can just say if the location is within the location that you set in the code, then go ahead and change the state of the LED. So that's pretty simple. We have the battery, we have the status lights, which are basic elements of the robot. But I do have something exciting to show you, which is this. Let me go to full screen here. We don't need any more code. I want to show you something. This here may not look like much, but it is a rotary encoder. So the 3D printer has a rotary encoder on it, and it has about, I got quick math in my head, 365 degrees divided by, it has about 72 stops in it, where it pulses to tell the microcontroller where it is located. This one is a little bit different. It has 600 pulses per revolution. So 600 pulses per revolution. So if as this shaft moves 360 degrees, it sends out 600 pulses. And that's how we're going to measure the distance that each wheel travels, based on the rotation of the rotary encoder and the ratio between the rear axis of the motor and the front axis of the motor. And we'll go into that in a few minutes. What's up, baby girl?
I want Mama.
She'll be home in 20 minutes. You see yourself? Look,
It's you.
look,
It's
yeah,
you.
look over here, look over here. Look at the green light. See the green light? Right here? That's you. No, point over here. Look. That green light is you.
And that's me. It's you.
Yeah. Do you want to go watch a little bit of TV while I finish up here? I'm telling everybody about the new little rotary encoders I got, the little motors.
But it's so shiny.
So shiny, yeah. Because it's new. I'll see you soon. I love this. This is proof that life happens, and it's amazing. She, as young as she is, she's 3 years old, and she loves everything that I'm doing with the robot. And it seems like she actually understands what I'm talking about. But anyway, so the motors that I have on the robot The rear axle rotates 18 times, and it's geared down to a differential that rotates the forward 10-inch wheel one time. So for every 18 revolutions that the rear axle does, the 10-inch wheel rotates once. So that means 600 pulses per revolution times 18 is one full revolution of a 10-inch wheel. And then you can calculate the circumference of the 10-inch wheel, and you know how far you've gone. So that is some relatively easy math that I have to do a little bit later on in order for the robot to drive itself. There's two more things that I have to integrate. I have the rotary encoders. I have to mount them. I have to connect the IMU, which is a 9 degrees of freedom IMU, and get those messages being sent and observed by all of this jazz. Has to be observed by this. I have to get the angular acceleration and all of the other basic metrics from the IMU. I combine that with the PID settings for the rotary encoders, the distance calculation, the distance between both wheels. This is getting complicated, but it's sort of not once you broke it down into several different steps. So once I get all of that information and get it published, this is a prime example of why I'm using ROS as my operating system. I can publish all this information to a mainframe or a home iteration of ROS, and it will take all that information and broadcast it out to everything that's subscribed to it. So I can take all of this information, broadcast it out on several different nodes, not wasting any more memory space than I need to, and calculate everything that I need to in order to move the robot forward. So, probably wondering, there's several people out there that's made robots, and they just hook their transmitter to it and start driving it around. Yeah, and I would argue that that's not a robot. That's a remote control car that looks funny. What I'm doing is I'm trying to make a very, very, very smart robot. So robot, by definition, is an intelligent mechanical machine or mechanism. So I posted before on my Facebook page. If you haven't followed me before, you can go to facebook.com/Cerebral Dad and follow me. But I challenge the fact that the hardest thing about building a robot is not the artificial intelligence, because you can connect several different nodes together and get some awesome results. It's getting that information into a manner that the robot can understand. And that's the challenge. It's more hardware than software. And I'm a software guy. I'm not a hardware guy. Rotary encoders? What the heck are they? I didn't know what they were 7 months ago. And I'm now learning what they are and how I can use them. They are so, so, so amazing. So we're going to be putting that on the back of the motor, putting those on. That's one of 4 pieces of the puzzle that I have to put together in order to make this robot drive by itself or through a computer input that I publish to the mainframe. Yeah, it's quite a challenge, but it's so much fun. This is so much fun. Okay. I have a challenge for you. As I'm working on all of this... Oh, wait, I wanted to show you something. I got a development board for the Arduino Mega, which is in the robot. This is the Arduino that I'm going to be using for this. And I got a development board that has a whole bunch of screw terminals. So what I can do is I can just, sort of like the fuse, the fuse panel that I have, I can just screw in the wires from all these random things into the Arduino, and they will be recognized. So this is awesome. I have to solder this all together. It'll take me about 40 minutes to do. And then I got a few of these, you know those hoverboards that the kids were like blowing up on a few years ago? Well, I got a few of those cheap batteries. One of them came damaged, so I have to return them. But I'm going to be using these 36 volt batteries in the meantime to lower the weight of the robot and increase the capacity, because these are the same cells as these are in here. Can you see that? See the bulge? See how perfect that is right there? They're the same exact cell in here, configured in a 36 volt pattern, 3.4 to 4.2 volts. So that means this is 42 volts fully charged. And I can charge that with my hobby controller right here. My hobby controller right here. I can charge this up, and then it'll be like I have a 36 volt source of a few of these. You see how many I have here? I do a 36 volt configuration with everything I have here, and it's a longer lasting battery. So that is one thing that I have. That is one thing that came in the mail today, so I hadn't had any chance to configure it. I'm going to be putting this together so I can get the rotary encoders installed. What else? I got one of these. This is a 36 volt 10 cell, meaning this is one cell 36 volts. Maybe it's, let's see, 1, 2. It's a one cell 36 volt. Let's see. Yeah, one cell 36 volt battery. This is going to be a 10 cell 36 volt battery, so it's going to last for about a week. It needs to run the computer for about a week. And I have the way that the battery is going to be safe for my children to be around, and I'm using a website that I'll show you in the next episode. We are going to be able to construct a battery that is not only safe but very powerful for the robot. Safety is the main goal here for building a robot in a household with small children. I'm just not willy-nilly building a robot here. So those are a few of the things that came this week that I'll be working on a little bit over the weekend, a little bit over the next week. I built a lot of this this code that you see here. It didn't take me very long. It took me to about 3 hours today to put all this together. I have to actually put it into the Arduino to see where everything's going. Another class that I'm going to build is a ultrasonic distance sensor. Distance sensor. I'm going to put that on the back of the robot so that when it's backing up, it can detect how far it is from anything, so it doesn't run into anything. This is also useful if it is running around and turning and its butt end of, because the driving motors are in the front. If the butt end swings around too fast, it can know exactly where it is in relationship to the wheels. So this is very important. Think about that. I mean, how much are you aware of your body? And have you ever thought about all of the different processes that are involved in sensing everything around you? I mean, we can drive a car, right? And a robot can barely, right? So we visualize the road, we can see speedometers, we can feel the gas pedal, we can feel the brake pedal, we can feel how fast we are going, we can feel how fast we are stopping. We can do all that. But let's rewind for a second. What does it take for a robot to do that? Can it feel how fast it's going? Well, it needs a 9 degrees of freedom. I am you that has an accelerometer in it that can measure g-forces. So if you have access to the g-forces that are publishing to a node somewhere, you have access to that. So the artistry involved is to get all of that information, tactile information, physical information, everything involved in what you need to autonomously drive something. Visual recognition. Let's say that there's a stick in front of you, or there's a puppy in front of you. How do you make the differentiation between the stick and the puppy? A stick you can drive over easily. A puppy, you might not want to drive over a puppy. So, visual recognition is quite a process in robotics, but it can be done. Everything that we're doing to this robot, we're doing exactly as we need to. Again, I want to do it the right way. This is how MIT is doing. This is how Boston Dynamics is doing it. They're using the ROS operating system to control their robots, and I wanted to make a proper robot. And this is the way I'm going about doing it. Of course, I don't have to use an Arduino. I can make my own microcontroller board and plug everything I need into it. But this is a development process. This is a development robot where I'm just learning about robotics and all the processes that are needed in order to drive the robot, make the robot think in an intelligent manner, respond to random occurrences in any process. So these are amazing things that humans can do that are seemingly almost impossible that robots cannot do and are a constant struggle in the robotics community. So these are things that I want to experiment with. I want to thank you for joining me today. This was a bit of a technical episode. Not much to see, but I wanted to show you that I am making improvements. I am programming my butt off, and when you make a robot, that's primarily what you're doing. You're programming a bunch of hardware to be intelligent, and I hope you enjoy that part, because the subtleties that we come up with and implement along the way are going to make huge differences, and you'll see. I hope to have a little bit of a video for you. I know I said I was going to give you a video this week, but as you can see, as I get interrupted, well, you know, life happens. My kids are going into school this week, and we're getting everything ready for them. Work is a little bit more important right now, so I have a lot on my plate. But I hope you enjoyed the content that I provided you with today, and I hope you feel encouraged to try something in robotics, because it's so interesting and so rewarding. Thank you for joining me. If you'd like to support my channel, please do so by going to the links below with the merchandise. And if you would like to make a one-time donation, I have PayPal links in there as well. Thank you. This has been live stream number 5 on, what is today? August 24th. The time now is 7:53. Again, thank you for joining me and joining me on my journey to building a true robot that can do something extraordinary. Together, we're going to figure out what that is and what our robot can do. Thank you for joining me. I'll see you next week.